Hello, welcome to Tennessee's At-Home Learning Series for Math. Today's lesson is for all our 8th graders out there, though all students are welcome to tune in. This lesson is the 18th in our series. My name is Candace Thompson, and I'm an 8th grade math teacher at Oakland Middle School in the Rutherford County School System. I'm so excited to be your teacher for this lesson today. Welcome to my virtual classroom. If you didn't see our previous lesson, you can find it on the Tennessee Department of Education website that I have pulled up here. You will scroll all the way down to Math Grade 8. You can find the lesson plans we're following, as well as the student packet with independent practice for your student. You can still tune into today's lesson if you haven't seen any of our others, but it might be more fun if you first go back and watch our other lessons, since we'll be talking about things we've learned previously. Today, we will be learning about how to use the Pythagorean Theorem to find the distance between 2 points on a coordinate plane. Before we get started, to participate fully in our lesson today, you will need paper, pencil, and a surface to write on. Calculator or calculator app is recommended. Graph paper is recommended, but not required. Okay, let's get started. Let's get warmed up. In lessons 16 and 17, we explored the Pythagorean theorem and its converse that allowed us to calculate the missing length in a right triangle and to determine if a particular triangle was a right triangle based on its side lengths. Today, we will explore another application of the Pythagorean theorem when we move the triangles onto a coordinate plane. Let's warm up by reviewing how to read and plot ordered pairs on a coordinate plane. You probably started learning this back in about 5th grade. Let's start with these 3 points or ordered pairs. We have 1, 3, 1, -1, and -1, 1. Now let's create a coordinate plane on our paper. If you have graph paper, this will be a little bit easier, but you can use regular paper too. We're going to plot the points. Let's look back at our 3 points. We had 1, 3, 1, -1, and -1, -1. Now remember that ordered pairs are listed as directions. You're going to start at the origin, 0, 0, and the values tell you how many units to move horizontally in the x-axis and then vertically on the y-axis to get the location of the point you want to put on the graph. Let's try one together. So our first ordered pair was 1, 3. This tells us that we move from the origin 1 unit to the right and then up 3 units. 1, 2, 3, and plot your first point here. Are you remembering how to plot ordered pairs? It's not unusual to forget whether you start horizontally or vertically, which is why we're taking a moment to practice. Now let's plot the next 2 points. You plot along with me. The next ordered pair is 1, -1. This tells us that from the origin, we're going to move 1 unit right and then down 1 unit to get our point 1, -1. Now for the third ordered pair, can you plot this one yourself? Give it a try. All right, let's see what you did. The third ordered pair was -1, -1. So this tells us that we need to move left 1 from the origin and then down 1 to get the location of this ordered pair. Does your graph look like this? Keep this graph handy. We're going to use it as we move to our lesson today. But here are a few things that I want you to remember. Write these down with me. And I'm going to actually write this down on the back of this paper. So go ahead and write down these key points with me. Ordered pairs are always listed as values indicating horizontal and then vertical. Directions from the origin. Okay, next point. An ordered pair can be represented this way. X, Y. And then finally, if you have more than one ordered pair, like we will today, they can be represented like this. X1, Y1, and X2, Y2. The subscript tells you or helps you identify which set of ordered pairs you are working with, like the first, second, third, so on and so forth. So those are our key points today. Are you guys feeling warmed up? Great. Let's start on today's lesson. So let's look back at the 3 points that we graphed on the coordinate plane. If we connect the dots, we can create a right triangle like this. So I'm going to use the edge of a paper so my line is somewhat straight. Okay. Our goal is to approximate the length of the hypotenuse. You can use a calculator to help you. So let's first find the length of each leg. So let's look at this horizontal leg. This length is 2 units. Let me get a different color just so it's not all the same color. Let's try green. So this horizontal leg here is 2 units, okay? What about the vertical leg? Right, so the vertical leg is 4 units. Now, from lesson 16, we know that we have a length of 2 sides of a right triangle. We can use the Pythagorean Theorem to calculate the length of the missing side, or in this case, our hypotenuse. So we can tell from the model we're looking for the hypotenuse, and we know that because it's the opposite side of the right angle. So you can write it this way. Solve along with me. So we're going to use a squared plus b squared equals c squared. Okay. So remember that A and B represent the leg lengths and C represents the hypotenuse length in the right triangle. Substitute in what we know. Remember that we square the numbers first before we add them by order of operations. So we have a leg of 2 and a leg of 4. And we're solving for that hypotenuse. So I have 4 plus 16 equals c squared. 20 equals c squared. Now, remember, to solve for the equation for c, we need to take the square root of both sides. So you'll want your calculator or calculator app to help you, okay? Now, I have mentioned this on previous lessons. If you don't have a student calculator like I'm going to be using today, if you will use your cell phone and make sure that your orientation lock is off, turn it horizontally, and then we're looking for the square root of 20. So you can just type in 20, and then you'll hit this button right here that has the radical with a little 2 in the corner. That means square root. And that will give you the same answer as if you use a student calculator that I'm going to use today. So the square root of 20 You can see you get the same thing either way. So if we round our answer to the nearest tenth, we would say that C is 4.5. So we would say that the length of the hypotenuse in this graph is 4.5 units long. 4.5 units long. Now, does that make sense given the context of this problem? Looking at the length on the model, it should have a measurement between 4 and 5 units long, and that is the longest measure of the triangle in this case, as it should be for the hypotenuse of this right triangle. Let's look at a second example. I'm going to show you a model of the right triangle on a coordinate plane, and we will determine the side lengths from the grid and use the Pythagorean theorem to determine the length of the hypotenuse. Let's see what we can identify from here. Now, let's look at the vertical leg. Look at the vertical leg. Talking about this here. How many units would you say that is? Correct. It is 4 units long. Okay. What about the horizontal leg? If you counted 5 units, you are correct. Great job. So now we have enough information to use the Pythagorean theorem to approximate the length of the hypotenuse. Let's give it a try. You follow along with me. So we have a squared plus b squared equals c squared. Substitute in what we know. Remember that we square the numbers first before we add according to the order of operations. So my 2 leg lengths are 4 and 5. So I have 16 plus 25 equals c squared. 41 equals c squared. Now remember, to solve the equation for c, we need to take the square root of both sides. You'll want to use your calculator or your calculator app to help you. So I'm going to use my calculator that I have here. Whoops, yep, 41. Let's round our answer to the nearest tenth. So we would say that the length of the hypotenuse is approximately 6.4 units long. Okay, so there's a challenge with the method we're using now. It will only work if the right triangle is situated in a way that we can read the unit length of the 2 legs. So there must be a way to apply this in such a way that will work for other types of models of right triangles. That way is called the distance formula. The Pythagorean theorem can be transformed to derive this formula. Let's see if we can follow along with this logic. I'm going to show you another model, but this time we won't count the units. We will identify the locations of the vertices by their ordered pairs. Take a look and make a sketch of this model here. Okay. So do you see that the points are labeled by their coordinate x and y, but without values? Let's talk about this together. You write along with me and think about what you are seeing on the model. Write these key points here, okay? So since line segment PR is a horizontal segment, its length is A. It's the difference between its x coordinates. Therefore, A is going to equal the distance between x2 and x1. Since QR is a vertical segment, its distance is going to be the difference between the y coordinates. So therefore, B is going to equal y2 minus y1. Okay? And so then you'll use the Pythagorean theorem to find the length D, the length of segment PQ. So what we get is that D squared equals A squared plus B squared. So D equals because we have to take the square root of both sides to get rid of that exponent of 2. So d equals the square root of a squared plus b squared. So we substitute the expressions from the previous statement for a and b, okay? So what that means, guys, is that d equals the square root of, now how did we get a? Well, we had to do x2 minus x1. So we have x2 minus x1 squared plus, how did we get b? Well, we did y2 minus y1, so plus y2 minus y1 squared. Whew, that was actually a brief exploration into a proof of the distance formula. Make sure you have this formula written down and label it distance between 2 points formula. I'll read it again. So d equals x2 minus x1 squared. Remember, that's just how we found the distance here. Plus y2 minus y1 squared. Remember, that's how we found b here. Okay, so let's see if we can use the distance formula to estimate the length of the hypotenuse. We need to know these things. Write them out for me. So let's do this. Let's do this. So we have, so the coordinates of P, I'll just show you this here. There we go. So the coordinates of P are going to be 2, 2. And the coordinates of Q are going to be 7, 7. Now let P be the first set of ordered pairs and let Q be the second set of ordered pairs. We will substitute into the distance between 2 points formula. Write this along with me. So we have D equals the square root of x2 minus x1 squared plus y2 minus y1 squared. Okay, so let's plug in our points. So we have, we'll label these accordingly. Let's do x1, y1, or let's do x2, y2, and x1, y1. Okay. All right, so we've got the square root of x2, which is 7, minus x1, which is 2, squared, plus y2, which is 7, minus y1, which is 2, squared. Now remember your order of operations. In this case, you're going to subtract before you square because of the grouping symbols. So that is going to simplify to 7 minus 2 is 5. So the square root of 5 squared plus 5 squared, which is going to be the square root of 25 plus 25. One more line, we're going to use our calculator to give me the approximate value of the square root of 50. And we're going to round to the nearest tenth. So I've got square root of 50. So my answer is the distance between those 2 points is 7.1 units. All right, so how are you feeling about this? Let's practice one more example. Follow along with me. Here's another grid. Take a look and make a sketch. See if you can read the coordinates of the endpoints of the hypotenuse. Okay, did you see the endpoints of the hypotenuse? Great. Now, if we read this graph correctly, this first endpoint right here is at -1, 1. So -1, 1. Okay. And our second endpoint here is at 4, -2. Now, we can decide that -1, 1 will be our x1, y1. So I'm going to put -1, 1. I'm going to put x1, y1. Okay. And then that means that we're going to have 4, -2 be our x2, y2. Okay. So by substitution, we can use the distance formula to estimate the length of the hypotenuse like this, right? And follow along with me. Okay. So we've got d equals the square root of x2 minus x1 squared plus y2 minus y1 squared. So d equals the square root of x2, which is going to be 4, minus x1, which is -1 squared, plus y2, which is -2, minus y1, which is 1 squared. Now remember the order of operations. In this case, you're going to subtract these before you raise anything to a power of 2 because I have my parentheses here. Okay, and we do what's in parentheses first. Also, don't forget the integer rules of addition and subtraction. So when you work that out, you are left with d equals the square root of 5 squared plus -3 squared. Also, don't forget here that when you square a negative, you are going to get a positive. So it would be d equals the square root of 25 plus 9. So d equals the square root of 34. Now use your calculator or calculator app to help you get the approximation round to the nearest tenth. So I'm going to do square root of 34 and I get 5.8 units. Great work. Let's practice one more. Okay, so let's think about this problem. I'm going to read it aloud and you think about it and look at the model. So Victor wants to find the distance between his house on one side of the lake. So here's his house. And the beach on the other side. Here's the beach. He marks a third point, forming a right triangle as shown. The distance in the diagram is measured in meters. I'll read it again and you think about what you need to do. Victor wants to find the distance between his house and the beach. He marks a third point, forming a right triangle. And the distances in the diagram are measured in meters. If we want to use the distance formula to find the length between the house and the beach, we can use the coordinates for each of those to substitute in. Follow along and write this example down with me. So let's say that 280, 164 will be our x1 and our y1. And that means that 1020 is going to be our x2 and our y2. By substitution, we can use the distance formula to estimate the length of the hypotenuse like this. Write and follow along with me. So the distance equals the square root of x2 minus x1 squared plus y2 minus y1 squared. Okay, so now let's plug in our values. So x2 is 10, minus x1 is 280 squared plus y2 is 20 minus y2, y1, 164 squared. Now remember the order of operations like before. In this case, you're going to subtract these numbers first because of my parentheses around them. So we have d equals the square root of 270 squared plus 144 squared. You'll want to use your calculator or calculator app to help with the squaring. So this tells me that the distance is the square root of 72,900 plus 20,736. So the distance between the 2 points is going to be the square root of 93,636. Now use your calculator or calculator app to help you get the approximation. Round your answer to the nearest tenth. And so we get 306 meters. So we would say that Victor's house is 306 meters away from the beach. Great job with that, guys. Very, very good job. All right, so those examples were pretty lengthy, so we weren't able to hit as many as I would have liked, but I hope that your confidence is growing in using the distance formula to find the distance between 2 points on a coordinate plane. After this lesson, if you want, you can use this website to find additional practice problems to work on your own. I really enjoyed exploring using the Pythagorean Theorem as the distance formula to find the distance between 2 points on a coordinate plane with you today. Thank you so much for inviting me into your home, and I look forward to seeing you in our next Tennessee's at Home Learning series.